Welcome back for part 3 of electric field mapping. Wanted to break it up so in case you want to watch one part or the other, you could. So now we're going to do part B, which is not along the central axis of the diagram, and it is 5 centimeters away from the positive charge. So let me go over here and just do my calculation over on the side. And you'll notice how symmetrical my diagram is. So my calculation for point E is also going to have some relationship to E, F, and G, all of the points that are not on the central axis. So here's my calculation. And remember, I'm not going to use 5 in here. I'm going to use my scaled distance, which is centimeters, this is meters. I'm going to use this scale distance in my formula here. So I get also remember, make sure you square your R in this formula. And putting my numbers into the calculator, I get 4.26 times 10 to the negative 11 meters here, meters for my scale distance right here. And then plugging that in here, remembering to square my R, I get 7.93 times 10 to the 11th newtons per coulomb. So that's the magnitude of the electric field due to the positive charge at point D. Now, what I'm going to do is I'm going to just get rid of this for a moment, clear myself some space. I'm going to move my ruler over here, and I'm going to rotate it. Whoops, I rotated around the wrong point. Start my ruler up here at D, and I'm going to rotate it to get to the center of the negative charge, and that is 13 centimeters. So I'm going to calculate one more time my scale. One times 10 to the negative 10th over 11.75 meters centimeters equals x over 13 centimeters, and that gives me 1.1 times 10 to the negative 10th. I'm going to use the same formula down here to calculate the size of the electric field. My constant, the size of my charge, and the square of the distance, and that will give me, and that gives me 1.2 times 10 to the 11th newtons per coulomb. And logically, looking at our answer, the negative charge should have a smaller field contribution at that point than the positive charge, and it is. This is almost 8 times 10 to the 11th. This is 1.2 times 10 to the 11th. So logically, that makes sense. So let me go ahead and clear out some of this stuff here, so we can draw in those vectors the right size and see how we add them together. Because these are not just straight additions, there are x and y components to some of these things. So the contribution from the positive charge, start with that, we'll make that the green arrow. At point D, electric field lines, again, go from positive to negative. So from positive means away from the positive charge. It will be directed upward. And the electric field contribution, let's change our color here, from the negative charge, see we used red last time, stick with the same color scheme here, from the negative charge, from positive towards negative, so I'm just going to point directly towards the negative charge, but it's going to be smaller, because remember our line was about 1/7 as long. These aren't to scale, but you get the idea. So what we need to do is we need to find the x and y components of this one, and the x and y components of this one, and add them together to get our total electric field vector at this point. Now, because this is directly above the charge, and I did that on purpose, this will be all y component. So for the positive, E positive x will be 0, and E positive y will be the total size of the contribution from the positive charge, which is 7.93 times 10 to the 11th newtons per coulomb. And for this one, the hypotenuse will be 1.2 times 10 to the 11th. Now, how do we find the x and y component? The same way we always did when we had triangles. So, back to the old triangles, we will have a y component, which is here, and an x component, which is here, to make this a right triangle, so we can find the size of the components. And you say, oh no, all we have is a hypotenuse. How are we going to find the sides? But we actually know more than that, because there are two similar triangles in this circumstance. So I'll use this to show you my similar triangle. Down here, across to my positive charge, and over to my positive charge. So this big brown triangle is similar to this little triangle right here. So if I find the angles inside my big brown triangle, then I can use those lengths. Remember, this was 11.75 centimeters. This was 5 centimeters because I measured those previously, to find the angles inside my triangle. So let me find this top angle right here. Oops. Find this top angle right here. So that is, let's see, I have an opposite and adjacent, so I'm going to do tangent. So tangent of theta is equal to opposite divided by adjacent. These are both in centimeters, which is good, because I can't have any units inside of my trig functions. I'm going to take the inverse tan of both sides, so I get the inverse tan of the tan of theta is theta, and the inverse tan of 11.75 divided by 5, my units cancel out, is equal to, is 67. Came out nicely. Degrees. So this is 67 degrees, this is 90 minus 67 degrees because it's complement, and this is 90. So back to my little tiny vector triangle up at the corner here. I now have this top angle, and I have my hypotenuse, so I can find my sides. So let me get rid of some of this writing here below. So I have some space here to do a little bit of calculation, and I will find my components. Okay. So to find the y component, this is adjacent to the angle, so I'm going to use the cosine. So cosine 67 is adjacent, which is x, that's what I don't know, over the hypotenuse, which is the magnitude of the electric field from the negative charge at point B. And I can do the same thing with sine, and that will give me y. Whoops, my adjacent side here is y, sorry. Let's fix that. y right here. This is the vertical side, which is opposite to my angle is right up here in my triangle right here. So this is my y side, and this is my x side. X over 1.2 times 10 to the positive 11, which again is the magnitude of my electric field at that point. So that will give me, and these are the two values for the sine and the cosine times the hypotenuse. Now what I have to do to finish adding my vectors together is I add the x and y components from the green vector to the x and y components of the red vector. So the x component of the green vector was 0, the x component of the electric field from the negative charge, which is the red vector, is this. So my total x component is 1.1 times 10 to the 11th, and it is pointed into the right, which is the positive direction, so it's a positive vector. My total y component is, the green vector is directed upward, it's positive 7.93 times 10 to the 11th. And the y component of my red vector is pointed down, so it's negative, and it is 4.7 times 10 to the 11th. So subtracting those two, I get 3.23 times 10 to the 11th. Remember, these are all newtons per coulomb because, oops, that's a C, because these are all electric fields. Now, to find the total vector in that direction, these are both positive. Let's draw our total electric field vector triangle. So positive is in the upward direction on my diagram, like this. The x component is positive, so that's to the right, like that. Not drawn to scale at all. And the hypotenuse will be something like this. So this was the x side of my triangle, which is this, 1.1 times 10 to the 11th. My y component is 3.23 times 10 to the 11th. So to find the hypotenuse, I do the Pythagorean theorem, and then to find the orientation relative to, in this case, the positive x-axis, I could do inverse tangent. And that will give me, then putting that in the calculator, I use Pythagorean theorem to find this, and I just eyeball my magnitudes. This looks very reasonable for hypotenuse based on the length of those two sides. Then I use tangent of this is opposite over adjacent, opposite side over adjacent side. Put that in the calculator, inverse tangent of both sides, so I get 18.8, and this red vector indicates the direction and magnitude of my net electric field. So 18 degrees from here, that particular length, that will be the net electric field vector at that particular point above the positive charge, off to the left of the negative charge at that point in space. So you can repeat the same process for any points that are not oriented directly on the central axis. The central axis, remember, is nice and easy because it's all positive axis. All x components, sorry. So that is how you find the net electric field vector at a point. And I left myself a reasonably clean map here. After you have all of your electric field vectors at all of these different points, then you will have So after you have a few values of the electric field calculated, and these are just rough estimates of the magnitude, I can actually calculate these, you'll have a whole bunch of electric field vectors, and you want to draw your electric field lines. So take a nice big thick line here. We start from positive and we go to negative, so we know this one will be pointed directly this way. And I'll put my arrowhead on it to show you how it's directed. And then here, I start on the charge, and I go tangent to each of the vectors as I get to them, kind of like connecting the dots with a little bit more math knowledge than you probably had when you first started connecting the dots. And then here, follow this one, tangent, tangent, tangent. So I could have curved out a little bit more on that one. From this point right here, and then coming from off the screen here. Oops, well, this was straight like that. Off the screen here. I go this way, and then here, starting with a positive, going out. And I didn't want that straightened, but here, and going out like that, and going like that. So ignoring the fact that the program straightened it automatically for those two. And again, here we'll take another, no, still going to straighten it. But you get the idea. Those would be my electric field, oops. Those would be my electric field lines. Got my arrowheads in here. Yep. All radiating out, away from positive, and in towards the negative right here. Here are my signs. And then for equipotential surfaces, you would start here. And you go perpendicular to each of the field lines. That's not very neat, but going along like that. And the next equipotential surface would kind of curve out a bit like that. And then the same thing for over here. Perpendicular to each of the lines as we cross it. And I'll spring a little bit there. And around like that. So we have these things, which are electric field vectors. We have the yellow that are electric field lines. And we have the orange that are equipotential surfaces. And that is an electric field map.